Our planet Earth is enveloped by a sea of air we call the atmosphere. This ocean of gases is not uniform, it's layered like a cake, with each layer having distinct properties. The layer closest to us is called the troposphere, our home turf for breathing, weather, and life itself. Above the troposphere lies a boundary, a transition zone known as the tropopause. Think of the tropopause as the ceiling of the troposphere. It's the point where the temperature stops decreasing with altitude and instead starts to increase. This temperature inversion acts like a lid, trapping most of the Earth's weather phenomena within the troposphere. The tropopause is a crucial part of our atmosphere, influencing everything from our climate to the way airplanes fly. But here's a curious thing. This atmospheric ceiling is not uniform. It's higher at the equator than at the poles. Why is that? To unlock this mystery, we must journey into the heart of Earth's energy balance and understand how the sun's warmth shapes our planet. Our sun, a blazing star millions of miles away, bathes our planet in energy. However, the Earth's curvature means that sunlight doesn't reach all parts equally. The equator, receiving direct sunlight, is like a stovetop burner on high. The poles, on the other hand, receive sunlight at a slant, like the edges of a frying pan, heating up less intensely. This uneven heating creates a temperature gradient, a difference in temperature between the equator and the poles. Warm air, less dense and full of energy, rises at the equator. This creates a zone of low pressure at the surface. Meanwhile, the colder, denser air at the poles sinks, leading to a zone of high pressure. This continuous cycle of rising warm air and sinking cold air is the engine of our planet's atmospheric circulation. The tropopause, that critical boundary in our atmosphere, is directly influenced by this temperature gradient and the resulting air circulation. Let's see how. Imagine a hot air balloon rising from the equator. As it ascends, it travels through the troposphere, where the air gets colder with height. Eventually it reaches the tropopause, the point where the temperature stops decreasing. Because the air at the equator is warmer overall, the balloon has to travel higher to reach this point. This is why the tropopause is higher at the equator. The warm air pushes it upwards. Now picture the same balloon taking off from the North Pole. Here, the air is much colder to begin with. As the balloon rises, it quickly encounters the temperature inversion that defines the tropopause. The tropopause is lower here because the air is already cold, and the temperature inversion happens at a lower altitude. This difference in tropopause height isn't just an atmospheric curiosity. It has profound effects on the way air moves around our planet, and ultimately, on our weather patterns. Remember that low-pressure zone at the equator caused by rising warm air? Well, the high tropopause contributes to this. The rising air expands as it reaches the tropopause, further lowering the air pressure at the surface. This low-pressure zone acts like a vacuum cleaner, drawing in air from higher pressure areas like the poles. This constant movement of air between the equator and the poles, driven by temperature differences and influenced by the varying height of the tropopause, is what creates our planet's global wind patterns. These winds in turn distribute heat and moisture around the globe, shaping our climate and weather. So, the next time you feel a gust of wind on your face, remember the invisible ceiling high above the tropopause. Its varying height, a consequence of our sun's uneven heating, is a key player in the intricate ballet of our planet's atmosphere.